Hello everyone, hope you are having a great day. My name is Kavathiya, a second year student of Pandit Deendayal Energy University studying computer science. I am from Team 4 and we were assigned the topic Deadlock and Concurrency in our operating system lab. So we prepared a website which simulates all the algorithm and we have deployed the website in Netlify. So what is concurrency? Concurrency is the execution of multiple instruction sequences at the same time. It happens in the operating system when there are several process threads running in parallel. The running process threads always communicate with each other through shared memory or message passing. Now, what is deadlock? Deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some other process. Consider an example when two trains are coming toward each other on the same track and there is only one track. None of the trains can move once they are in front of each other. A similar situation occurs in operating systems when there are two or more processes that hold some resources and wait for resources held by others. So let's go and check out which all algorithms we have implemented. In concurrency, we have implemented Peterson's algorithm, producer-consumer algorithm. In Deadlock, we have implemented Banker's algorithm and Tanning Philosopher algorithm. So let's check out Peterson's algorithm. Peterson's algorithm is considered a standard low-level algorithm for two-thread mutual exclusion. We will learn what is critical section. We begin our consideration of process synchronization by discussing the so-called critical section problem. Consider a system consisting of n processes P0, P1 up till Pn-1. Each process has a segment of code called a critical section, in which the process may be changing common variables, updating a table, writing a file, and so on. So what is the criteria for Peterson's algorithm? First is mutual exclusion, second is progress, third is bounded waiting, and fourth is portability. So let's execute the Peterson's algorithm. So in here we are having three states. First is entry state where both the processes are present. Then we are having critical state and exit state. Let us move the process P1 to critical state. Process P2 cannot enter the critical state because P1 is already present. Let us try adding the process P2 to critical state. We are getting error, which means that law of mutual exclusion is satisfied. So let's move P1 to exit state so P2 can enter the critical state. Here flag indicates which process is in critical state and turn tell which process it is to enter the critical state. So let us move to our next algorithm, producer and consumer. The producer-consumer problem is a classical multi-process synchronization problem. That is, we are trying to achieve synchronization between more than one process. There is one producer in the producer-consumer problem which produce some items, whereas there is one consumer that is consuming the items produced by the producer. So let us execute the algorithm. Here we add 10 to the total space, 2 to produce and 1 to consume. So if we click on producer, it produces two process 1, process 2. If we click another time, we get process 3, process 4. Then if we click consumer, it consumes the one process. That is, process 4 is consumed by the consumer. Process 3 is also consumed by the consumer. If process exceeds the total space, we are getting error saying space is full, cannot create more. And if there are no producers left, which means all the processes are gone, then we get an error, producers are not enough. Let's move to our banker's algorithm. The banker's algorithm is a resource allocation and deadlock avoidance algorithm that tests for safety by simulating the allocation for predetermined maximum possible amounts of all resources, then makes an S state check to test for possible activities before deciding whether allocation should be allowed to continue or not. Let's execute our algorithm. Here we can add process by using plus sign and delete process using minus sign. We will calculate the save sequence for 5 processes. After filling all the resources, allocation, max and available, we hit the calculate button. We get the save sequence as P1, P3, P4, P0, P2, which means if we follow this sequence, then we will get no deadlock. Moving on to our final tiny philosopher's problem. The tiny philosopher's problem states that there are 5 philosophers sharing a circular table and they eat and think alternatively. There is a bowl of rice for each of the philosophers and 5 chopsticks. A philosopher needs both the right and left chopstick to eat. A hungry philosopher may only eat if there are both chopsticks available. Otherwise, a philosopher puts down the chopstick and begins thinking again. So let's execute this algorithm. Here we are having 5 philosophers and there are 5 spoons present on the table. Each philosopher needs 2 spoons to eat, otherwise they cannot eat. Let's simulate. Here we can see that this and this philosopher is eating and this philosopher are waiting. So if when they first and that third philosopher has already taken their meal, then this and this philosopher will eat their meal and this will eat afterwards. This is our About Us page. Here you can see the developers who created this website. The X factor in our website is the bot we created to help users know more about operating system concepts. And finally, bye bye.